Welcome back. Let's see what other interesting problems we can solve now that we know simple derivative rules like the power rule, the derivatives of sine and cosine, derivative of e to the x, and some basic principles like constant multiple and sum and difference rules. That makes it easy to solve problems like finding the slope of the function at a given point, but it also makes it possible to solve the opposite question. In this proposal, I want to find what point on the graph of a given function has a certain slope, or where does the tangent line do certain things. And in this case, we want to determine the values of x where the given function has a horizontal tangent line. Well, that means there's a place, we're going to try and attempt to find a place where the tangent line has or runs like this. Let's think about that for a minute. Sometimes with the equation or function you're given, you should already just start to picture in your mind what the graph of that function basically looks like. You don't have to know a lot of the details, but the basic shape you ought to be familiar with. In the first one, we're given a cubic function, and the leading coefficient is a positive number. Hopefully we're familiar enough with that kind of a function that we know the basic shape is going to run either like this, where it starts low and ends high and doesn't do a whole lot of bending in the middle, but it could also be like this, where it starts at the low end, bends twice, and then continues up again. Okay? So in the case like that, it's possible there would be two such places where the slope or the tangent line runs horizontally. If the graph ended up looking like this, there would be two such places. One that would be like kind of like that, and one about like this. But either case, the way calculus is going to help is that we actually know that a horizontal line has a slope of 0. Okay, so the phrase horizontal tangent line means the slope of the tangent line is 0, and because it's a tangent line, calculus is used, and the derivative that produces the slope of the tangent line must equal 0. So this yields to the slope, which is always found by the derivative, is going to have to equal 0. And so this basically boils down to, I could retranslate this question and say, determine all the values of x such that the derivative of this function is equal to 0. Well, now that we've learned some basic differentiation or derivative rules, that's going to make the left side of this equation easy to figure out. We're going to compute the derivative of g. I actually encourage you to pause the video right now and try and work that out for yourself. And if you've already tried it, now we'll use the power rule. And if I multiply 1/3 that's already as the coefficient times 3, it's going to be 1x squared. The derivative of x squared is 2x. The derivative of 15x to the first would be 15 minus 15. X to the 0, but x to the 0 we normally would not write because it's just equal to 1. And the derivative of 6 is 0, and we're not going to write plus 0. We're just going to leave it empty. So this is my derivative. If I want to know where the slope of the tangent line is equal to 0, I need to know where the derivative is equal to 0. So I'm just going to simply solve this equation. 0 equals x squared plus 2x minus 15. If you're lucky, you can just solve this by factoring. If it doesn't factor, you could resort to things like the quadratic formula for a problem like this one. But let's see if I can just factor this. I think I can go here and try x plus 5 times x minus 3. And that does factor down from there. And since I'm solving now x plus 5 times x minus 3 is equal to 0, we can just solve it by taking the two factors, each equal to 0, and finding that x is either -5 or x is 3. So there's actually 2 points, like I was predicting. The graph is going to end up being shaped like this, and this first point has an x-coordinate -5 because it's the leftmost point, and this point is going to have the x-coordinate of 3. It's the rightmost point. You were not asked for the full ordered pair, so we're going to stop right here and just know those are the 2 values of x. I encourage you to try this one the same way now. Maybe just pause the video and solve this one. You're trying to also find the horizontal line, so you'd want to solve when does the derivative of this function equal 0. I encourage you to pause the video, and when you come back, I'm going to have the solution worked out for you. And I've worked this one out for you now. The premise is we want to find where the slope of this function is equal to 0. So I've worked out the slope formula, the derivative of this function. Remember, 2e to the x, the derivative would be 2e to the x, because the function e to the x is its own derivative. The term 4x, this is 4x to the first, so the derivative would be 4 times 1, x to the 0, and x to the 0 is 1, so we can just leave it as 4. And we need to solve the equation 2e to the x minus 4 equals 0. It'll take 2 steps, adding 4 to both sides, then dividing both sides by 2 to arrive at e to the x equals 2. And to solve for x, we would have to write the log on both sides. The natural log of 2 equals the natural log of e to the x. And that means that x is the natural log of 2. Perfectly fine to leave your answer like that, guys. But on the calculator, that would be 0.693. Here's one more problem that's kind of interesting. I have a function that I don't know the whole story about. It's got one coefficient marked with an unknown letter k. So the function x squared plus kx plus 1 is f of x. And it says find the value of k so that the line over here, y equals 2x, is going to be a tangent line to this function. Okay, let's just think about what that is asking us to do here. I think I'm going to draw as much of this as I possibly can, maybe just up here. Okay, so let's actually draw the line y equals 2x. It is going to be a straight line with a slope of about 2, with a slope of 2. So I'm going to draw it about like this. Okay, that's roughly what that line would be. Let's think about the function over here a little bit. Do you know what shape it is? Regardless of what number k would be replaced with, this is a quadratic function and it's got a leading coefficient of 1. So the basic shape is going to be an upwards parabola like this. Now, another thing I know is that this function ends in a 1, which means if you think about it, if the y-intercept is going to be 1, because if x were 0, y would be 1. So this parabola has to go through 0, 1, which is 1 point above where the line crosses the y-axis. Okay? Now, let's think, could I draw a shape like this parabola, going through this point that would eventually be tangent to this line? I think I could do that more than once, but let's just see if I can do it even once here. I'm going to attempt to draw a parabola through that point that will eventually be tangent to this line. Let's see if I can draw it. Here, maybe it would come up and be tangent like this. Maybe it would even happen down here further. Or maybe it would happen up here. Okay, so, but I know I can draw it at least once, where it's probably going to be tangent to this line. Well, let's think about what happens when a function is tangent to a line. When they are meeting each other, obviously the y-coordinate of this graph must be the same as the y-coordinate of this graph. Okay? By doing that, that's just going to force the two functions to coincide. Okay, so if I were to just for a minute think of this as g of x, just so I can name them. if this graph is going to be a tangent line to this graph, that means the graphs have to be touching. So one of my thoughts in the plan down here is that in order for this to occur, the function and the line must intersect. If they're going to intersect, the value of f of x must equal the value of g of x. So I'm just going to write that equation here. In order for this to occur, x squared plus kx plus 1 would have to match what the line is doing, which is, it's the rule y equals 2x. So on this side, I've got an equation that basically says solving this for x would allow me to find where on the x, what number on the x-axis is this two graphs touching. Now, two graphs could touch by actually crossing through and not being tangent. So in order for them to be tangent to one another, they must touch, and when they do touch, they must have the same slope. Okay? And as soon as you see slope in calculus class, you got to think derivative. All right? So my other plan is I need to know when does the derivative of f coincide with the derivative of g, because when they are intersecting, they must have the same slope. Okay? So my other equation is going to be the derivative of f. I'll just use my power rule. Now you got to be careful in the middle term there, but the derivative of x squared would be 2 times x. Now this is a constant times x. So if you think about that with the power rule, 1 comes down, multiplies by k, and then it's going to be x to the 0. So I think the next term is just simply going to be k. And then the derivative of 1 is 0. But on the other side, I want the derivative of y equals 2x. Well, the derivative of 2x is 2x to the 0, or just 2. So I'm just going to circle here now. Here's two equations that must be true when the graph of the function f of x is tangent to the graph of this line. So now I just have to solve this kind of like a system of equations. Each equation has x and k. Right? So the ultimate goal is to solve for k. But what I think I'm going to do is I'm going to solve this bottom equation for k and substitute it into this other one so I can at least combine the equations. This could be solved k equals, if you look at that carefully, k would equal 2 minus 2x. And you can now take that and replace it up in the other equation. So we're going to go up here now. This one comes across, and replacing k with the quantity 2 minus 2x. And there it is. So read it again. This is x squared plus kx plus 1 equals 2x. This equation can just be solved for x, but let's expand out the parentheses right there. So that would lead to x squared plus 2x minus 2x squared plus 1 equals 2x. This is going to be a quadratic equation, so let's get it all on one side and have 0 on the other side. But look at that, I'll subtract 2x here, and I've got another 2x to subtract it from there. So now I've got x squared minus 2x squared. That leaves minus 1x squared plus 1 equals 0. And I don't even need to factor this. I can just solve for x squared by subtracting 1, dividing by negative 1, and then taking the square roots of 1 and saying x could either be 1 or it could be negative 1. So I was correct that there's actually two times this will happen. Now, we were asked to find the value of k, so we're not quite done. This is going to tell us there's two answers, but to get the actual value of k, remember that over here k was equal to 2 minus 2x. So the first value of k, I'm going to call that k1, is 2 minus 2 times positive 1, which would be 0. So the first value of k is 0. The second value of k is going to be 2 minus 2 times negative 1, which is going to end up being positive 4. The second value of k is 4. So my k is either 0 or k equals 4. I encourage you now to try this by graphing those two functions along with y equals 2x to see that they in fact are both tangent to that line. It would be the function x squared plus 0x plus 1, and the other one would be y equals x squared plus 4x plus 1. Check and see that they both have that line as a tangent line. I hope this is helping you guys complete the rest of lesson 2.2. We'll see you back here in a day or so, and we'll talk to you more then. Have a good rest of this e-learning day.